Welcome you all to the session 2, which is on predictive analysis. So we have with us from Danfoss Industries Private Limited, Mr. Veeranagouda Patil and Mr. Christian Svendsen. They will be talking about pressure pulsation analysis of axial piston pump using computational fluid dynamics and experimental validation. A brief about Mr. Veeranagouda. Mr. Veeranagouda Patil is a technology specialist at Danfoss Industries Private Limited in high pressure pump division with over 10 years of industrial experience, including 3 years at Danfoss. He specializes in design and engineering simulations to support the development of high performance products. Veer currently leads the design and development of axial piston pumps for critical applications such as reverse osmosis, humidification, gas turbines, and firefighting. Prior to Danfoss, Veer worked as a senior application engineer at Simerics Inc., where he provided CFD simulation support and training for turbo machinery, fluid power, and automotive sectors. Over to you, Veer.
Thank you very much, and good morning, and each and every one of you here. Veer, you can just call me just a Veer, cut it short, so that it's very comfortable. I come from Danfoss, as Sir mentioned. Before I get into my presentation, I would like to thank FPSI for the opportunity, and special thanks to Taj Vivanta Hotel, and especially, and one more thanks to the SWRO Hall. I'm a Hubli guy. I would like to say in a native language, Sara Mastaiti. It's very beautiful. So with that positive note, I would like to talk about my work on pressure pulsation analysis of axial piston pump using computational fluid dynamics and experimentation. Just to start, from yesterday we have been hearing all of these axial piston pump, and I'm also axial piston pump guy, but today it is a little bit different. We talk about on the hydraulic, not only hydraulic side, we talk about on water side. I'll explain in a minute what is exactly that mean by. For the next 20 minutes, you are going to hear about axial piston pump for a desalination application, and how the pressure wave pulsations are generated in the axial piston pump and how they propagate it. And then next, you are going to hear about what are the way to analyze these kind of pressure pulsations. And the third thing is, you can also, how to mitigate these kind of pressure pulsation in hydraulic system. That's the topic of my presentation today. As I see that most of we are talked about axial piston pump, especially for for the oil hydraulic industry, right? But we have in the Danfoss we have two divisions. One is power solution, another one is climate solution. Power solution guys, they actually design and develop the products for the oil industry, and we come from a climate solution, and we have a product for for the desalination application. We have a wide range of products and which will help them to produce the fresh water, especially for the desalination industry. And our pumps are running throughout the world, all 100 countries, and they are running 365 days to produce the fresh water. Now, there are a lot of advantages why we are going for axial piston pump for for this kind of application is because traditionally you have a centrifugal pumps, which are in rotating nature, right? Axial piston, centrifugal, which are multi-stage pumps. But you see that, right? Any performance curve of axial piston pump, you say that you have to operate it for the best efficiency point. If you move left and right of it, you basically lose the efficiency of it. That's why the innovative product like axial piston can be used. One of the attractive feature for this kind of a positive displacement pump using in axial piston pump is that you get a fixed flow rate independent of the discharge pressure. No matter what you have pressure, 60 bar, 80 bar, 120 bar, you get the same discharge flow. And top of it, it's only function of the RPM, and that you have in control. And that is what you have to do to meet your requirement. But there are a couple of issues here, even axial piston pump, even for the centrifugal pump. One is that, as Bull Engineering Director talking yesterday, cavitation. Sir, it is a 2-decade or multi-decade problem, and still we are living with it. And we don't know how to solve it, and we learned how to deal with it now, okay, only by some other means. On top of it, you have another problem called pressure pulsations. This is inherently present in all of the axial piston pump. You can imagine a pump is rotating in a 1500 RPM with 9 pistons. Every single second it is drawing the liquid in and then expelling it out, every single second. Let's say that one pump have 4 pistons which are in the discharge side, you will have 4 pulsations. And 4 pulsations into 1500 times, that is the number of a pulsation it produces in single minute. And imagine these kind of a pumps runs for 365 days throughout the decade, 10 years. And you can imagine the damage they causes to the hydraulic system. This is exactly why it is important to mitigate these kind of pulsation and meet certain kind of compliances. Now, in terms of if you don't address, there are a lot of challenges like resonance, operation losses, and so on. And as you already know. Now, okay, when this kind of a pressure pulsation is a discrete form, it forms, what exactly happens when they travel into the downstream of the pipe? You can imagine one situation that you have a wall and these pulsations, they hit it, and then it can completely reflect back. It can partially translate, or it can, completely go, or completely reflect. These are the 3 situations it can happen. So acoustic guys can help us to understand how these pressure waves can, affect us, right? So there is a term called acoustic impedance. So this acoustic impedance basically helps us to understand what exactly each interfaces at the end of the discharge pipe, how these pressure waves reflect. When they reflect back, there will be a formation of the standing waves in the pipe. When we have a standing waves, these waves basically, if they matches the frequency of the structure and the fluid, then there will be resonance. So we have to be extremely careful how to model all these kind of pressure waves. So we identified mathematically three interesting cases. One is completely assume that you have a pump and that generates the pulsation, and they just pass it. There will be no reflection coming out of it. Okay, that's the situation, and you can call it as a reflection coefficient 0. Let's say another situation, you have a wall, and then it just basically hit it, and it can partially come back. Or strongly it comes back with the same phase. That is another case with R is equal to +1. And then third case is R is equal to -1, where you have, it just hits the wall, and then it strongly reflects, but with a change in the phase reversal. So that is the third effect we have. So if you don't mitigate this kind of a pressure pulsation in hydraulic system, what exactly happens? That is the resonance, what I talked about. But API 674 guideline says that if you want to use this kind of APP pumps in a hydraulic system, you have to follow some limits. So it says there are two conditions. The peak-to-peak maximum pressure variation of a pump at individual frequency, component of the frequency, should not cause the cavitation. Let's say that you have an inlet pipe and these pulsations are causing, and if the pressure goes below the vapor pressure of the liquid, and the cavitation forms, and that don't want to happen. And the second thing is that at the discharge side, the same peak-to-peak pressure pulsations, it can basically cause the relief valve lifting. So these are the two conditions, they say that, and we have to meet them if you want to use the same axial piston pump in a hydraulic system. Now, how do we model this one? One thing to model is that you can perform a CFD simulation as a virtual test bed. You take the same pump, use it in a virtual environment, like using a Computational Fluid Dynamics CFD software called Simerics, and then you model the inlet pipe, you model the outlet pipe, and you put the same monitoring point the way it is in the experimentation. And after that, you try to solve all the flow, all the cavitation and all the turbulence and everything. And now, coming to the next step of the computational fluid dynamics, and I know that one of the most difficult part of modeling this kind of machines in virtual environment is because of the translation of the mesh motion. The piston is rotating, it is also translating because of the swash plate angle, right? So such kind of handling mesh motion is very complex. So there are guys sitting next wall here, the Simerics guys. You can go and talk to them how the hell they are going to model these kind of complex mesh motions. Coming to my actual simulations, what we have done, first we try to have the same pump and fix it for the two conditions and run for the different RPM and to see the performance of it. Okay, how the volumetric efficiency look like, how the hydraulic power look like. Okay, and the second case is for the fluid dynamics engineer that, okay, now I said that there are waves, pressure pulsation waves, they just act like a sound pressure waves, right, sound waves, and how do we model mathematically these kind of things? So there are three things we tried. One is Just like as a beginner, any computational fluid dynamics over here, that if your boss asks you to simulate what you do, you basically set inlet pressure as the constant 3 bar, outlet pressure as a 60 bar. But you can see what is the result of it, okay, in the next coming slide. The second case is that mathematically you can model these pressure waves so that you tell to mathematically you tell that there will be no reflection coming back. Everything smoothly propagates into the discharge pipe or an inlet pipe. So that is the second case we tried. And the third case is mimicking the exact case what it is there in the test. In the test, you have a pipe and then you have a needle valve, right? So exactly the way we have done it. And finally, in order to mitigate these pressure pulsation, so to understand how much these pressure pulsations are affecting, right, or what frequency these are there, that's exactly what we have done, the pressure spectral analysis of it. Now, coming to the CFD methodologies, this is again meshing, and it's all the Navier-Stokes equation with the simple S equations and stuff like that. And this is one of the best software you can use it for all rotating machinery, I would say. Coming to the main method, what we have worked on is that to mimic these pressure pulsations to propagate very smoothly, not exactly having anything. So we have used a model called resistor capacitor model. In that resistor capacitor model, you can basically set whatever the number. If R equal to 0, you say it can basically allow the flow to travel very smoothly. But there is a problem. You cannot use directly. You have to do some user-defined expression to include these kind of things here. Now, this is the Danfoss experimental setup. How does it look like? You have a pump, and then it's connected to the inlet pipe, and then there is a booster pump there, a centrifugal pump as a booster pump to rise it to 3 bar pressure. And then at the outlet side, you have a straight impedance tube. This is the impedance tube what we have. We call it the impedance tube, and it is around 2 meters, and you have 7 sensors in that tube to measure the pressure. And then these pumps are operated using variable frequency drives to change the pressure. Coming to the result part of it, you can see that all of these rotation speeds ranging from 500 to 1500 RPM, the volumetric efficiency, you typically get it close to 98%. And in terms of the hydraulic efficiency, most of our pump varies from, you have from 82% to 93% of the energy efficient. And this is far, far higher than what you typically get it in a centrifugal pump. That's why we call it, these are the most energy efficient pumps. Now, just fluid dynamics, and you have to see some colors. And you can see on the top, a guy who set fixed pressure, okay, 3 bar inlet and 60 bar at the outlet. You can see when the piston is rotating and it just pulsation generates, and that if you just fix the 60 bar at the outlet, there will be waves coming back as well. You can see some dark spot there, which is happening. So again, the incident waves comes, and then there will be a reflection of and translation of the waves, which is happening, even though we are setting just a 60 bar to go out of the flow. So that's exactly what's happening with the fixed pressure bar, with the fixed pressure. Another case is anechoic termination using Simerics resistor capacitor model. You can basically model the same way what it actually look like. It generates the pulsation, but nothing comes back. Everything smoothly propagates in a discharge pipe. That is the second animation we have. And the third one, you are mimicking exactly the same condition as the test. So in that case, you have a needle valve, and that needle valve also has some impedance, right? The waves will hit, and some of the wave will reflect back. This is exactly, you can see what exactly happening in the waves here. Coming to quantitatively, okay, how can I be sure that what's really happening? You can just monitor all the sensors here, and I have monitoring points in the same locations. And you can see that the red color is the test one, okay, which is we have done. And the second case is just to reflect exactly what we have done in a CFD. It is a needle valve with the green curve. So you can basically see the trend and everything it is trying to capture. So it has a closest agreement with the needle valve. The second option, anechoic boundary condition, right? With the anechoic boundary condition, I say that just R is equal to 0. In that case, you have basically not exactly capturing every trend, but it is very, very close to what we have with the needle valve in CFD. And the third case, as a beginner, if you set just a fixed pressure boundary conditions, you have too much of off. You can see that how the standing waves are, they are completely away from, this kind of. If you have this kind of results, what we can suggest to system designer? How can we design? How can we show our accuracy here? That's the problem. And once we do this kind of analysis, what is the next step? Next step is for a system designer, and you take the same pressure pulsation and do the spectral analysis of it to understand its frequency and the amplitude of it. So you can see the one first image here. This is the one shaft and revolution completely. And it's a periodic, and you chop it into the only one pocket of the piston. And then it is in the time domain, whatever you are getting the pressure and the time and pressure. And then you try to put it in a MATLAB code and do the fast Fourier transform, and then get the peak-to-peak pressure and the frequency.
You have another minute. Sorry, you can just speed up another minute.
Yeah.
Thank you.
And then you have basically at the inlet, you have time, and then if you discretize, and if you put it in a MATLAB, you can compare basically how the CFD and API limit. API limit also has the same formulas. You can use them and see. There is important things happening here, basically. At up to this one, you need certain things. That is a dampener. If you want to use the same pump in a hydraulic system, you need this dampener. That's the message here. And this has been done using computational fluid dynamics. The same thing happens at the outlet side. Outlet side, you have one pocket, and then you try to compare the CFD and API limit, and it says that up to 1300 hertz, you need a dampener. With this, I'll like to tell about computational efficiency of it. We used around 128 cores and resolved with a very good accuracy of the time and the mesh. And finally, there are two messages. One is for the general audiences. If you don't know, the axial pistons are used for a hydraulic, and especially for the water, and we have that solution for you. And for the computational fluid dynamics engineers, that be aware of what kind of boundary condition you are using it. It's very, very important, and it is more important than your mesh, because this dictates the physics of it. And the third thing is, if the system designers are here, you have to use the dampener to mitigate this pulsation at the inlet up to 1 kilohertz, at the outlet 1.3 kilohertz. Still, you can mitigate these pulsations to use efficiently. These are the references, and I thank each and every one of you for the humble patience. Thank you very much, sir. And I'm open to any questions.
Yeah, thank you, Mr. Veer, for your nice presentation. I have two queries.
Yeah.
The first one is, since you are mitigating the pulsation of a piston pump, and here the average pressure or steady state pressure you are considering at 60 bar.
Yeah.
But piston pressures are high pressure pump. So do you have any visualization that as the pressure increases, so whether the pressure pulsation is going to get dampened or what?
Yeah, that's a good question. Sir, first, to answer you that, we have typical requirement for desalination industry for these axial piston pumps are 60 bar, 80 bar, and 120 bar. Okay? And we know that the customer requirement that is 60 bar, and for that 60 bar, this is exactly what we have done it. Now, to mitigate this one, if you want, it is all the setup, how does the desalination setup look like, right? If you are operating for 80 bar, you know that you are operating for 80 bar. And for that, you need to do the same analysis and get the frequency at what it is operating. Because the pulsation levels at each pressure, when you change it at the discharge, it is going to change. And this is very bad for the hydraulic system. So what the conclusion here you get it basically is that for this particular condition, a working condition, you have to use this kind of a dampener up to this frequency.
Means actually, or in other way, whatever I asked, in other way, whether the pulsation is geometric parameter dependent or operational function parameter?
Yeah, it is
dependent?
mostly on the operational point of view. If you reduce the RPM and if you reduce the the discharge pressure, you don't expect this kind of a huge pressure pulsations there.
Okay, and the second one was that this you are measuring this pressure pulsation experimentally.
Yes.
So obviously to measure as the amplitude of pulsation is I think in the range of 5 to 10 bar.
Yeah.
So what kind of pressure sensor here you have used for measuring this amplitude?
We have used something called a Kistler sensor, Kistler fast sensor. Very expensive one. It's like a tablet. You can swallow it. It's very small one, but a very expensive one. Yeah, that's exactly what we have used.
It's pressure transducer.
Yeah.
Okay. Over to the audience.
Okay, no more questions?
Yes, there are one question.
Question. Please.
So I'm Ravinder from Epiroc Nasik. So question is, generally piston pump manufacturers don't recommend to go below 10 CST of fluid viscosity. So fluids are, water may be having near to 1 CST. So how you are basically making sure that the boundary film is properly made in terms of, let's say on the interface of barrel and the port plate and on the swash plate and the pistons. So how the life of pump is ensured, because that's a very critical parameter when we talk about selecting a piston pump for a hydraulic application.
Yeah, very good question, sir. Again, this is, as you rightly said, these kind of pumps are used for very high saline water, right, for a seawater. And all the properties are completely different than what you have it. So then you have to use a special kind of a filters here before our pumps. So then if there are some kind of a material, changes in the fluid properties, and it's going to really hurt our pump as well. And that's answer for it. And in our case, everything is taken care by filters. And when you go and inspect our customers, that most of the pump failure happens not because of our pump, it's because of the way they are handling the filters. The way whether if there are abrasive particles which are getting into this, if they are not careful enough to install the downstream of the upstream of their pump, and then it's going to hurt our pump. Yeah.
So my question was basically on the viscosity part, not on the filtration.
I think here viscosity doesn't affect much for us. Okay. In our kind of, we operate it at 25 degrees Celsius seawater, and we don't see any problem with the viscosity here.
Okay, then can you tell a basic difference between a hydraulic axial piston pumps and a water-based? Because in waters, we don't use these kind of pumps. In a high pressure washer kind of application where we used to generate 200 bar of pressure, we use generally a triaxial piston pump, basically a reciprocating type. Interpump group makes that. So that's a different kind of pump where the lubrication of pump is ensured. So, so that's my query, how the lubrication of this pump is ensured even with the water.
We try to have a super duplex material, and the height of the clearance, I don't want to disclose what kind of a clearances we have in between the valve plate and the port plate, and what kind of a clearances we have between the cylinder and the bushing. That is a Danfoss property. But you're right that one of the important thing about this one, the clearances, how we manage, and the timing, how intelligently you connect between high pressure side to the low pressure side of this one, that where we stand, and what kind of corrosion resistance material you are using it to resist for, to have a good life of, because you can see that seawater is very corrosive, right? And it can damage the entire pump in very short time. And then one of the headache for till today is the cavitation one. You can imagine 60 bar in microsecond, it comes to 3 bar and below the vapor pressure, and then it damages the cylinder bushing. And we have a special bushing arrangement for it to control that one. And we replace only the bushing if there are damaged. And we have intelligent grooves which can help us to reduce the transition of the HP to LP and LP to the high pressure side.
Okay.
Thanks a lot.
Thank you. I think other questions offline, please. We are running out of time. Yeah, thanks.
So anybody asks you how was FPSI, please say must I3. Thank you.
Thank you very much, Veer. Just a minute. Hold on. Veer.
Oh.
Mitali, can you please...